Little intro. Next up, we have another talk that was rescheduled from the 2022 JMM special session on recent advances in packing. Our speaker is Matt Fickus. Professor Fickus is a professor of mathematics at the Air Force Institute of Technology. Professor Fickus's research is in applied harmonic analysis, frame theory, and compressed sensing. Today, he will tell us about harmonic Grassmannian codes. Please take it away, Matt.
Thank you, John. Thanks to all the organizers. Always a little bit of a bummer to not be able to see all you folks in person, but hopefully we'll get back to that very, very soon. In particular, for the AMS session, it's always a good idea to write a paper with like all the organizers of the session so that they kind of have to invite you as the only like co-author that's actually not an organizer, kind of get like a guaranteed talk. It's very appreciated. There is a slight amount of news on this cover slide here. The news here is that John and I actually now have a common affiliation. So if you pay federal tax dollars in the United States, I don't know if you like the stuff I do or not, but now you're getting John to do it as well. So your tax dollars at work today, sort of double time. So what I'm going to be speaking about in general is new constructions of these objects we call equi-isoclinic type fusion frames. I know a lot of you have seen this background before, so I'll go through it pretty quickly. My apologies to use that haven't. What we're going to have are three numbers here. I'm always going to list them in this order, D, N, and R. What they're going to represent are D is going to be the dimension of some sort of vector space, some sort of Hilbert space that I'm going to be working in. And the third number, R, is going to be the dimension of the subspaces I'm working with. The middle number, N, is going to be the number of those. So I'm trying to arrange n subspaces of a d-dimensional space where each one of those subspaces is of dimension r in sort of the nicest way possible, okay? And I'll try to explain more formally about what I mean by that. What we're going to do is for each one of these subspaces, I'm going to pick an isometry onto that. In other words, I'm going to pick an orthonormal basis for that subspace, and I'm going to stack the vectors of that orthonormal basis as the columns of that matrix. And then there's this bound here. That's actually a generalization of the classical Welsh bound. That basically tells you how well you could do. And if you could arrange all these subspaces to be mutually orthogonal to each other, you could drive the left-hand side all the way down to zero. But when things are too big, when you're basically trying to cram too many subspaces of too high dimension in a given space, you can't quite achieve zero. And the best you can do is hit this lower bound. And the important takeaway from this is the best you can do is arrange the subspaces so that when you take the projections onto those subspaces and add them up, you get a constant multiple of the identity. That's one thing you need. That's what we call a tight fusion frame in the frames biz. And then you have this other property, which Gary was just talking about, equiangular tight frames. This other property is sort of like a generalization of equiangularity to the situation where the subspaces are not lines, but rather r-dimensional subspaces. And what you do is you take this thing that's called the Gram matrix. So you take, for example, two of your spaces, your subspaces, you take an orthonormal basis for each, and you take this cross-gram, which actually computes the inner products of all members of the one orthonormal basis with all members of the other orthonormal basis, and you arrange that as a little R by R matrix. And remarkably, in order to achieve equality in this bound up here that I just circled, you don't just need tightness, you need this second condition. And what this second condition says is that all of these cross-gram matrices are basically a common scalar multiple of a unitary matrix. They are very hard to visualize, these objects, because pretty much most of the non-trivial examples, those with, for example, and all of those where the subspaces has dimension greater than one, they occur in spaces of dimension greater than 3. So we can't just be walking around in R in the way that we physically perceive our universe and just run into them. But these are extremely restrictive conditions in here. And so anytime we can find some of these guys, which seem like they have no business even existing in the first place, we get a little bit excited. And so that's the general question I'm trying to address here. I'm not going to come up with anything close to an answer one way or the other, but this part of our community is sort of obsessed with this idea of trying to characterize those D, N, and R for which these objects exist. The reason we really care about them is from a compressed sensing perspective, they have what's called minimal block coherence. So you can kind of think about it as that I have a lot of subspaces in a given Hilbert space. And for some of those subspaces, I'm not telling you which ones, I pull a vector out of those subspaces. I'm not telling you which vectors. And then I add them up and I just present you the sum of those. And then I ask, hey, can you tell me what subspaces you chose vectors from and what those vectors are. And it seems like a very hard problem. But as long as your subspaces are designed sufficiently well, in particular, have small block coherence, of which EITFFs have minimal block coherence, you can solve this problem, not often, but still remarkably often, in particular, if you only pick a few subspaces to begin with. And you can actually solve it practically, not just a matter of mathematically. You can use real algorithms to actually do it. From a more pure math perspective, every one of these equiangular type fusion frames is a Grassmannian code. So if you take the space that's called the Grassmannian, which is the set of all R dimensional subspaces of D dimensional space, a code in that space is an arrangement of n objects, in other words, n subspaces, each of dimension R, so that the minimum distance between any pair of them is as large as possible. And the distance we're using when we're talking about equi-isoclinic type fusion frames is something called the spectral distance. Now, there's a number of basic facts here. Whenever you talk about this problem, you can basically have some simple constructions of equi-isoclinic type fusion frames, and particular ways to take some EITFFs and convert them into other ones. One is you can take something called a Naimark complement, which basically keeps the same number of subspaces and keeps the spaces to be of the same dimension, but it changes the dimension of the ambient space that you're actually working with. Another kind of simple trick that you can do is you can take two equi-isoclinic type fusion frames that have the same number of subspaces, but they might have different ambient dimensions, in other words, different Ds, and they might have different dimensions of subspaces, different Rs. And as long as the proportion of the dimension of the subspace to the dimension of the ambient space remains constant, you can actually do this direct sum trick. This is not hard to prove. You literally just sit down with direct sums and prove that you get a larger equi-isoclinic type fusion frame. There is also this other trick that is due to Hogar, that was the mathematician who was being referenced in the last talk, where you could take complex or perhaps quaternionic examples of these objects and do a trick with them to convert them into either complex into real or quaternionic into complex, and then maybe also into real. But when you do so, you double the dimension both of the ambient space and of the dimension of the subspaces. And from that, that's sort of a hint as to how you do the construction. You basically represent a complex number by a 2x2 real matrix, and you represent a quaternionic number by a 2x2 complex matrix. Because all these tricks are sort of very well known in the community, the things that we seek most after are sort of those equi-isoclinic type fusion frames that are new from that perspective. In other words, if I gave you some known construction and then said, you got all this bag of tricks, you can take Naimark complements, you can take direct sums, you can convert complex into real and quaternionic into complex. Factoring all that into account, what is still new after all of that fact? And so one way to measure this, I'm not saying this is the best way, is, for example, to look in situations where there are no common factors between the dimension of your subspace and the dimension of the ambient space. Those are particularly interesting for us. One way to achieve that is when the dimension of the subspace is 1, and those are equiangular type frames. And to be clear, I am still, personally, I know a bunch of us, a lot of the organizers, are very interested in new constructions of equiangular type frames. I wish I was giving you a talk about new constructions of equiangular type frames. I just don't have any at the moment because they're very, very hard to find. But if you find them, please write it up and please let us know. We'd be very, very interested in those. Okay, those for me personally are still my most wanted object, basically, period. Okay, but on top of that, there are a lot of EITFFs that we're just starting to become aware of in recent years. Some have been around for a while, but the awareness of it on our part is fairly recent, that you cannot construct, for example, from equiangular type frames in some combination of those previous tricks, i.e. Naimark complements, direct sums, and Hogar's tricks. Some of these are classical. Some of these are in Lemons and Seidel's original paper, and it's a little hard to, on the topic of equi-isoclinic subspaces, and it's a little hard to parse it because they're not going to use the term tight frame. I mean, that's a tight fusion frame. That's a relatively recent construction, but Etaoui made me aware of this very recently. Etaoui is a leader in this field, and so he has a construction of a real EITFF 552 and then an 863, and he found this infinite family a couple of years ago where the number of subspaces and the dimension of the ambient space are the same. but then the dimension of the subspaces themselves is 2. So they're kind of really close to being equiangular type frames, because equiangular type frames have one-dimensional subspaces, and these, not being lines, they're planes. They're still pretty small subspaces. He also has a construction of quaternionic EITFFs, and when you apply Hogarth's trick to them, you get complex EITFFs of this size and this size. And then Joey, Emily, and Dustin, I believe, by going through some quaternionic madness of a different sort than the way I was just talking about, also came up with this really interesting recent construction of 15 three-dimensional subspaces of 21-dimensional real space. And so we have a relatively a growing but still kind of small list of these. And what I'm hoping to convince you of is a more general technique that is obtained by taking a known technique for constructing equiangular type frames, trying to generalize it to the fusion frame setting. And the payoff here is we get a couple new infinite families to add of EITFFs to add to this list. Okay, so the idea is sort of a generalization of this concept of what's called a difference set. And I'll come back to this in a moment. This is a very technical slide. I'm not expecting you to parse this whatsoever. I'm just trying to let you know that there is theory to back up everything that I'm just telling you. And the name of this talk is Harmonic Grassmannian Codes. That is also the name of a publication on Archive that we put up end of December, early January. If you want any of the details, I'm just advertising that. Go look at that, and it can provide you all the details. Let me try to explain what I just had on that very technical slide in the context of an example. So underlying this, there's going to be a group. And in this example, I'm just going to pick the group to be Z mod 5, the group of integers modulo 5. So just 0, 1, 2, 3, 4. And then it has a Pontryagin dual. It has a Fourier basis. And that comes from basically identifying, you can identify that itself with Z mod 5, and any number in Z mod 5, I'm going to identify with a homomorphism from Z mod 5 into the complex unit circle. And basically, if I stacked all these homomorphisms as the columns of a matrix, I get something that's called the character table of this group. And the conjugate transpose of that would be called the discrete Fourier transform of size 5. Very, very classical stuff. What's not so classical is this idea that I'm going to take what we call a small type fusion frame, which I'll explain what I mean by that again in just a moment. And we're going to do this modification to it to produce a larger type fusion frame. So what I'm going to start off with here is a tight fusion frame that consists of 5 subspaces for 2-dimensional complex space. And so I'm going to list those 5 subspaces. I'm going to give a basis for each one. Now, what is weird here compared to what most of us have worked with before in the context of tight fusion frames is it is not a requirement that all the subspaces have equal dimension. For the small tight fusion frame that we're building, they don't have to all have equal dimension. In particular, in this case, 4 of the 5 subspaces have dimension 1, and 1 of the subspaces has dimension 0. And one of the weird things about this theory is you actually have to pay honest attention to subspaces of dimension 0 in this case. So I almost have like a blank here where I'm like indicating, I don't know what a basis for this is. A basis doesn't actually exist. But what for each one of these remaining subspaces, each of dimension 1, I'm giving you a basis for them. So I basically just have 4 lines in 2-dimensional complex space. Now they form a tight fusion frame. And what I mean by that is that when you take the projection onto those 5 lines, one of which is dimension 0, and you add them up, you get a scalar multiple of the identity. Okay. What's crazy about this construction is if you take this matrix, the small tight fusion frame, who's, and I'm taking what's called its synthesis operator, the guy whose columns form bases for these various subspaces. And you take a transpose of it, you turn it on its side down here. Then what I get is a matrix whose columns are actually, I guess I'm taking its adjoint to be more precise, a conjugate transpose. You get a matrix whose columns are actually orthogonal to each other. And when they're properly scaled, if you put these 2 factors together, you get an orthonormal basis for one subspace. And if you act upon it by a abelian group of unitary matrices, what you can do is you can generate other subspaces. And what I'm actually doing when I worked with that earlier example was I had 5 subspaces, 1 of dimension 0 and 4 of dimension 1, but I had an underlying group of the integers modulo 5. And so I kind of have subspace labeled by group element 0 and subspace labeled by group element 1, etc. This matrix has roots of unity showing up in it. And those roots of unity are indexed by the group in the exact same way. And because this omega in this particular example is a fifth root of unity, this matrix that I'm just circling here again is actually a 4x4 unitary operator of order 5. And so the idea is that I'm going to take one two-dimensional subspace of C4, a four-dimensional complex space, and then I'm going to multiply it on the left by this unitary of order 5. And I'm going to get then 5 subspaces. I'm going to get the operator to the 0 times that subspace, the operator to the 1 times that subspace, operator to the 2, etc. And you can then plot them here. The hue in this particular picture is actually the phase of the complex number. And what I have is an orthonormal basis for subspace 0, an orthonormal basis for subspace 1, an orthonormal basis for subspace 2, 3, and 4. And because of the fact that all these subspaces are obtained from the initial one by acting on the left by this unitary group of operators, when you form what's called the fusion gram matrix, you get a very nice pattern. So what the entries in this matrix are actually indicating are those cross-grams, things of the form phi n1 times phi n2. So I'm taking one of the two-dimensional bases for one of my subspaces, a two-dimensional, a two-element basis for one of the other subspaces, and then I'm taking the inner products between all of them. And those are the guys that I need to be nice in order to form an equi-isoclinic type fusion frame. But because there is this group structure underlying this, then what happens is the actual big gram matrix that we have here, the collection of all these cross grams together, actually has a block circulant structure. And so if you look down this first column and you take those 5 2x2 cross grams and you just shift it down by 1 unit, you get the next column, okay? And basically the way to think about this construction problem is I am trying to arrange my subspaces so that this matrix that I have here, the gram matrix of all of them, is very, very nice. And basically by building symmetry into the construction, by using group theory underneath of it, what I basically ensure is that if I can make the first column nice, then I can make all the other columns nice automatically. That's just the big idea. It's an old idea. It's gone back through in what's just called regular old harmonic frames before you do harmonic fusion frames, but it indeed generalizes to this setting. And what we actually have a result in that paper that's on the archive that basically says, you are going to come from, you're going to have a type fusion frame that arises from a small type fusion frame. Like on the couple slides ago, I had this guy down here that had 5 two-dimensional subspaces of 4-dimensional space coming from 5 subspaces of 2-dimensional space, 1 of dimension 0 and 4 of dimension 1, a big type fusion frame coming from a small one. Basically, we have a theorem that guarantees that that will work in general if and only if your gram matrix has this block circulant structure. In other words, if you have a first column and you obtain the other ones by shifting it down. When this occurs, we say your subspaces form what's called a harmonic type fusion frame. And we refer to the small type fusion frame as literally the small type fusion frame. All right, none of that theory in itself is characterizing equi-isoclinic type fusion frames. It's about just type fusion frames. And so you might ask, well, can these actually be equi-isoclinic? Can these be optimal packings with regards to the spectral distance, i.e., can they give you arrangements of subspaces with minimal block coherence as valued for compressed sensing? And the answer is, yeah. This actually generalizes the idea of what's called a difference set for a group. But basically what happens in this case is if you build a bigger type fusion frame from one of these smaller guys, the resulting thing you're going to get is going to be equi-isoclinic if and only if when you take the projections onto the smaller spaces, I'll do an example of this in just a second, and take its Fourier transform, that what you get is something that is a constant multiple of a unitary, okay? Let's go back to this example where I had these 5 subspaces of 2-dimensional space for my small type fusion frame. And then I did this trick where I took a conjugate transpose and then multiplied on the left by this group of unitaries to make the bigger one. If you take these smaller subspaces here, so one was dimension 0, 4 were dimension 1, and you take their projections, I get basically 5 2x2 projections, one of which is rank 0, one of which just is all the 0 matrix, and 4 of rank 1. So P0 is just the zero matrix, and P1, P2, P3, P4, indexed by the group itself by Z mod 5, they're all rank 1 guys. And then what I'm going to do is this really weird idea. I'm going to take those projections and I'm going to take an entry-wise discrete Fourier transform of them all. And that's what this sum is right here. And so when you look down here, what I've actually done is, yeah, I've actually taken those 5 matrices, I've multiplied them all by roots of unity, and I've added them up in the normal Fourier way. And you get this thing. And what that previous theorem on the previous slide tells you is that this way of building a large type fusion frame from a small one, it's going to produce equi-isoclinic type fusion frames if and only if this sort of Fourier transform of your projections is always a constant multiple of a unitary, which in this particular case, it actually is. And it turns out the example I've been discussing for you actually is an equi-isoclinic type fusion frame of 5 two-dimensional subspaces of 4-dimensional space, which is pretty wild that it happens. In the special case where the projection matrices are just 1-by-1 matrices, well, a 1-by-1 projection is either just a 0 projection or a 1 projection. And for those of you that are aware of the classical theory of different sets in a group, this construction reduces to that in that specific case. Now, what's remarkable is we were able to actually use this idea to produce 2 new infinite families of equi-isoclinic type fusion frames. Turns out that they're harmonic, turns out that they're constructed in this method, but that's not really the selling point. That's just the means to the end. We actually care about the actual equi-isoclinic type fusion frame. So you can basically take patterns of we basically ripped apart small examples and then we're like, what's the small type fusion frame in this case? Can we identify a pattern, generalize, prove the theorem? And so we have one infinite family here where if you give us any prime power, we get Q subspaces, each of dimension 2, of a space of dimension Q minus 1. When Q is 5, you get the 4, 5, 2 that I've been having as the running example throughout this entire thing. These seem to be new infinitely often. Whenever Q is a prime power that's congruent to 1 mod 4 and is at least 19, we weren't able to find any previous examples of existence of this in the literature. And then there's a second construction that's kind of related, but it actually produces Q subspaces of space of dimension Q, both being planes as well. When Q is congruent to 1 mod 4, this is very closely related to a previous construction of at tau e that I mentioned on a previous slide. But when Q is congruent to 3 mod 4, these seem to be new. Okay. So there's other stuff along these lines that I won't go into any detail, but even though the construction is inherently complex because you're kind of multiplying by all these roots of unity, with enough symmetry, you can actually build real things from this. And we got, just as sort of an example that this technique might have some legs to it, we were able to actually build a real EITFF where the subspaces are actually 3-dimensional, not 2-dimensional. That took some doing. It's a very technical construction, but 11 3-dimensional subspaces of real 11-dimensional space. That's our first indication ever that a real EITFF or complex EITFF with those parameters even exists, let alone being harmonic, but we use the harmonic theory to build it. There's some other stuff that relates to conference matrices that came out of this as well. So just the last bit, this is available on archive, again, under the same title that the talk is. Google Works. I'm actually displaying these slides through Edge, Microsoft product. I'm really impressed. So if you don't want to use Google, just Bing it and then go out for a walk and listen to your Zune. It's available. Any search engine will bring you there. Because I know all the organizers of Codex, I think all the speakers at Codex should start a new sport, which is the organizers of Codex are awesome. Thank you guys for doing this seminar. They always try to think of questions. I've been on the back end of this a little bit. And they always try to think of questions to ask the authors at the end so that somebody asks us a question. Okay, it's a very nice thing to do. It's a normal thing that you do whenever you organize a meeting. I, at the very end here, want to snipe those questions. I want to anticipate them and be like, nope, I've already thought about it. I'm going to answer it. You guys got to think of another question right here on the fly. So you might be thinking, hey, man, this works to produce equi-isoclinic type fusion frames. Can it actually be used to produce equichordal type fusion frames in the Conway-Hardin-Sloan sense? And yeah, it does. It actually recovers some of the ones that Emily observed. It actually also recovers some of the ones that Zahner observed coming from Vivids. It actually gives you a general machine that if you take the small type fusion frame to be equichordal and you do this harmonic trick to it, the bigger guy is equichordal as well. Stuff that is still in progress. for different sets. There's been a lot of numerical work that basically says, we've looked for different sets and here they are. Now can you actually try to construct them? We are just starting to try to do that seriously for this work. And we don't have anything that we're making public yet, but that's something we are very much interested in. And then we're also interested in using this idea or something like it, where the underlying group is not an abelian group, but rather a non-abelian. All right, thank you very much for your time.
Thanks so much, Matt. All right, let's smash that reaction button again and hit the end of the recording.